Algorithms are the backbone of computer science and programming, serving as precise, step-by-step procedures for solving problems or performing tasks. These powerful tools take input, process it through a series of well-defined instructions, and produce an output. Understanding algorithms is crucial for anyone looking to excel in the world of computing and problem-solving. Let's dive into the core concepts that define algorithms. Time complexity refers to how long an algorithm takes to run, often expressed using big O notation. Sorting algorithms, such as bubble sort and merge sort, are essential for organizing data in a specific order. Recursive algorithms solve problems by breaking them down into smaller, similar subproblems, while divide-and-conquer algorithms split the problem into smaller parts, solve them independently, and then combine the results. These approaches are particularly useful for tackling complex problems that can be broken down into simpler components. These algorithms play a crucial role in many applications, from database management to search engine results. This approach can significantly improve efficiency in problems with overlapping subproblems, such as finding the shortest path in a graph or optimizing resource allocation. And Dijkstra's algorithms are essential for solving problems involving networks, relationships, and interconnected systems. These algorithms help us navigate complex structures, find shortest paths, and analyze connectivity in various applications, from social networks to transportation systems. This process of decomposition allows us to focus on solving individual components before combining them into a complete solution. It's often helpful to use pseudocode or flowcharts to visualize the algorithm's logic and structure before diving into actual implementation. We start by verifying the algorithm's correctness with small, simple inputs. Before moving on to more complex test cases, this may involve refining the algorithm's logic, choosing more efficient data structures, or applying advanced techniques like memoization or parallelization to improve performance. It's important to remember that optimization should be balanced with readability and maintainability, as overly complex solutions can be difficult to understand and modify in the future. This helps identify and fix any logical errors or edge cases that may have been overlooked during the initial design. Searching algorithms like linear search and binary search help us find specific items within a dataset quickly and efficiently. Different problems may require different data structures, such as arrays, linked lists, trees, or graphs. By understanding their core concepts, evaluating their complexity, and exploring different types and strategies, we can develop powerful tools to tackle a wide range of challenges. Whether you're sorting data, searching for information, or solving complex optimization problems, algorithms provide the framework for efficient and effective solutions. As technology continues to advance, the importance of algorithmic thinking and problem-solving skills will only grow, making them invaluable assets in our increasingly digital world. The choice of data structure can significantly impact the algorithm's performance and complexity. The first step is always to clearly define the problem and identify the inputs and desired outputs. This helps us understand the scope of the task and determine the most appropriate algorithmic approach. While not always guaranteed to find the best solution, greedy algorithms are often fast and can provide good approximations for many problems. They're commonly used in optimization tasks, such as finding the minimum spanning tree in a graph or scheduling jobs. For example, an algorithm with O complexity grows linearly with the size of the input, while one with O complexity grows logarithmically, making it more efficient for larger inputs. This approach is particularly useful for solving puzzles, such as the unqueens problem or Sudoku, where we need to explore multiple possibilities to find a valid solution. Space complexity, on the other hand, measures how much memory an algorithm uses during execution. Balancing these two factors is crucial in designing efficient algorithms that can handle large-scale problems without consuming excessive resources. First and foremost, algorithms must be finite, meaning they must come to an end after a limited number of steps. While some algorithms may not require any input, they should always produce at least one output. This input-output relationship is what makes algorithms so versatile and applicable to a wide range of problems. Lastly, algorithms must be effective, with each step being basic enough to be carried out, whether by a human or a computer. This ensures that our procedures don't run indefinitely, consuming resources without ever reaching a conclusion. Secondly, algorithms require definiteness. Each step must be clear and unambiguous, leaving no room for interpretation or confusion. This clarity is essential for both human understanding and machine execution. Another key characteristic of algorithms is their ability to handle input and output. When we evaluate algorithms, we consider two primary factors: time complexity and space complexity. Now let's explore some common types of algorithms that form the foundation of computer science. Recursion and divide. Conquer strategies are powerful techniques used in many algorithms. Dynamic programming is another important algorithmic technique that solves problems by breaking them down into simpler subproblems and storing the results for future use. Greedy algorithms make locally optimal choices at each step, hoping to find a global optimum. Backtracking is a problem-solving technique that builds candidates for solutions incrementally and abandons those that fail to satisfy the problem constraints. Graph algorithms, including breadth-first search, depth-first search, when it comes to problem-solving strategies. Algorithms provide a structured approach to tackling complex challenges. Next, we break down the problem into smaller, manageable steps. Choosing the right data structures is crucial for efficient algorithm design. Testing and optimization are essential parts of the algorithmic problem-solving process. Once we have a working algorithm, we can focus on optimization. In conclusion, algorithms are the fundamental building blocks of computer science and problem-solving.